Hello, fellow YouTubers, fellow builders, inventors, experimenters, collectors of antique radios, and workshop philosophers. I have a nice little project to show you today. It is a solenoid-powered walking beam DC electric motor. And boy, that is a mouthful. I built many DC motors over the years, and they've all been the armature motors. They've all had armatures and brushes, and they've been either 2-pole or 4-pole motors. This is my first attempt at a solenoid-powered motor. And believe it or not, it did demonstrate quite a few principles of basic mechanical engineering. Here's what it looks like. This can often be built from parts you find around your home or find around your garage. It's a lot of fun to put together, and it took a little experimentation to get it running efficiently. The central component of this motor is, of course, the solenoid. That's what furnishes the power. So let's begin by talking about the solenoid. What you see here is a typical solenoid. It's just a cylinder wound with many, many turns of wire. When current is passed through the wire, the cylinder becomes an electromagnet and draws in a piston like this. The solenoid furnishes power in one direction only. All it can do is draw the piston in. For the piston to return to its original starting position requires some external force. Usually it's a spring, but in the case of my motor, it's simply inertia. Let me charge this cylinder, and you can see how quickly the piston is drawn in. It's almost instantaneous. Anyone who's been around a dishwasher or a washing machine while it's filling with water has no doubt heard the mechanical clunking noise of a solenoid operating the water intake valve. All washing machines and dishwashers use solenoids. Also, the solenoid is absolutely essential in the operation of a pinball machine. The operation of a solenoid electric motor is a lot like pushing someone on a swing. Force is only applied at the beginning of each swing cycle, and then inertia and gravity take over to return the swing to its starting point, where it gets another burst of energy to begin the next cycle. The point is that no force is applied continuously throughout the cycle. And this is much the same with the solenoid motor. In the rotational cycle of the flywheel, at a certain point the solenoid produces a burst of energy that starts the flywheel moving. And then inertia takes over to return the flywheel back to that point where it gets another burst of energy, which starts the flywheel moving. Inertia brings it back to the same point. And this occurs over and over. Now what I'm saying is that the flywheel receives no continuous energy. And that's the reason why this type of electric motor, the solenoid electric motor, has very little practical application. It's a lot like the Jacob's ladder. Very interesting, but of no practical use to any scientist, mad or otherwise. Well, now that I've given my motor a nice introduction, I bet some of you are wondering if it actually works. And let me assure you, it really does work very well. My solenoid is rated at 12 volts DC, but I've run the motor anywhere from 10 volts up to 30 volts with no problems. I think the solenoid has quite a heavy winding. I paid $6 for it, and it came from All Electric Surplus here in Van Nuys, California. Okay, on with the demonstration. Well, as you can see, my solenoid motor really rocks. In fact, if I gave it enough voltage, I think it would literally tear itself apart. If you want to build a really efficient and very impressive solenoid motor, there are certain things you have to watch out for. Number one, the timing of the solenoid is very important. And also all the parts have to work together in a certain way. Let me give you some tips on construction. After some experimentation, I realized that one full rotation of the crank should translate into one full piston stroke. One full rotation of the crank translates into one full piston stroke. Being careful, of course, not to let the piston bottom out or fly out of its cylinder. And then I realized that I want the power stroke to be applied when my crank is in the 7 o'clock position. When my crank is in the 7 o'clock position, I arranged it so the solenoid piston would be fully extended all the way out and ready to be charged to provide the power stroke. Now the way the power stroke is timed, I'll show you on the back of my motor. Turning my motor around, you can see how I operate the micro switch. I have a little angle bracket attached to the same shaft as my flywheel. Each revolution of the flywheel makes the bracket strike the micro switch. Timing is easily adjustable by loosening one nut and rotating the bracket around the shaft. The shaft passes through a 1/4-inch ball bearing, which I have press fit into the wooden support. Friction is kept to an absolute minimum. At first it may appear that this is really a very simple device. It has few moving parts, and it looks a lot like something a kid would assemble in the 1950s from an old-style erector set. However, when it comes down to making the parts and assembling something like this, there are a lot of variables to contend with. For instance, the length of the walking beam, the position of the fulcrum on the walking beam, the stroke of the solenoid, the length of the stroke, the power of the stroke, the strength of the solenoid, the timing of the solenoid. Then you have the length of the connecting links, the weight of the flywheel, and probably a lot of other variables I'm not even aware of. What I would really like is for a student of mechanical engineering to give me a comment telling me that he or she could design this whole thing on paper mathematically, never touching a drill press, a hand tool, or a piece of material. Now I know this can be done. Unfortunately, Mr. Dillon and I are just not up to the task. But I hope we have inspired someone out there to build their own walking beam solenoid DC motor. It's a lot of fun. Well, that's it for now, folks. I want to thank you for listening, and Mr. Dillon thanks you for listening. We will see you again next time.